Right. So I hope you had a good Thanksgiving break. Welcome back. So yeah, I came a bit early to write down all the stuff from the previous lecture, right? So there's the definition of the Tutte polynomial. It satisfies the dilution contraction recurrence. And it's like a universal function on matroids, which, like every other function of matroids which satisfies dilution contraction, is a specialization of the Tutte polynomial. In particular, the number of independent sets, the number of bases are specializations, as well as the characteristic polynomial. And if you look at the special case for graphs, which is what originally, this class is where the Tutte polynomial was first defined, then you get all these kinds of different specializations. So 2, 1 gives forests, 1, 1 gives spanning trees, 1, 2 gives all connected subgraphs, 1 minus t comma 0 gives the chromatic polynomial, 2, 0 gives acyclic orientations, and 0, 2 gives strongly connected orientations. And finally, 2, 2 gives just 2 to the power of number of edges. Yeah, so, and last time we computed the Tutte polynomial of the complete graph on 3 vertices pretty easily, right? So the answer was x squared plus x plus y. And today I just want to start with finishing this computation and actually applying what we got here to get all this extra information about the graph from the just general properties of the Tutte polynomial. So yeah, let's just go through all these specializations and check that what we get is actually correct. So what is t of 2, 1? Yeah, so let's say I take this particular graph and then plug in 2, 1, and then you just to tell me what's the number and whether it's correct or incorrect. 7. And then that's the number of forests. So how many forests does G have? You can have no edges, or 1 edge in 3 different ways, or 2 edges in 3 different ways. So that's 7. 1 plus 3 plus 3. Okay. How about t of 1, 1? 3. Is that correct? Yeah, that's the number of spanning trees. So there's only 3 possible spanning trees. You just remove every edge. T of 1, 2. Yeah, maybe I should just do this substitution. 1 plus 1 plus 2, that's 4. What is supposed to be 4? The number of connected subgraphs. Right, yeah, so you can take any spanning tree, or you can take all 3 edges. That's going to also be connected. That's 4. All right, how about t? What's the next one? T of 1 minus t comma 0. That's actually tricky. 1 minus t squared, 1 minus t plus 0. Yeah, that looks familiar, right? That was the characteristic polynomial of the braid arrangement that looks like this. And it's also the chromatic polynomial, right? So if you try to, well, basically, if you multiply this by t, t times this would be, yeah, so what is the chromatic polynomial? If I take my graph, I choose one vertex, and I have t options for this, and then I have t minus 1 options for this, and t minus 2 options for this, and t minus 1 times t minus 2 is precisely here. So it works. All right. The next one is 2, 0. T of 2, 0 is 4 plus 2 plus 0 is 6. That's the number of acyclic orientations. So how do I get 6 acyclic orientations? I see. So you can choose a sink in 3 different ways, either this or this or this, and then once you have chosen a sink, let's say this is a sink, then this edge could go either this way or this way. I'm not going to create any other sink. Okay, so 6. P of 0, 2. P of 0, 2 is, okay, so a strongly connected orientation means that you orient the edges so that you can get from any vertex to any other vertex. Yeah, so you can either make a clockwise or counterclockwise cycle, so that's why it's 2. And finally, C of 2, 2 is 4 plus 2 plus 2 to the power to the number of things. Yeah, so to me this is kind of magical. And yeah, so and last time I kind of well, I mentioned the theorem that this polynomial is well defined. So it looks like I can make some choices along the way. I can at any point I can choose an edge to contract or delete, and maybe I'm going to get different answers if I choose different edges. Well, and the theorem was that actually no matter what are my choices, I get just a single polynomial to every associated to every matroid. So it would be nice to have an explicit formula, just a closed formula. If I give you a matroid, which is non-recursive, but like explicit. So here's a theorem, which is due to Whitney in 1932 or something like this, which is basically, well, he formulated it for graphs, but for matroids, it's very similar. So you take the sum over all possible subsets of edges of subsets of the ground set, and then take x minus 1 to the rank of E minus the rank of A times y minus 1 to the size of A minus the rank of A. So these two notions, this is called the corank of A, and this is called the nullity of A. So it's called the corank nullity formula. Yeah, I think so. Yeah, it's the famous Whitney. So let's try an example. Let's say I take this graph here, and what do? I need to take, let's say, my matroid comes from this complete graph on 3 vertices. Example. Then I'm supposed to take a sum over 8 sets. So A could be the empty set. So first of all, what is the rank of E? Which is the same as the rank of, yeah, say again? Yeah, so the rank of E, which is the same as the rank of the matroid, is equal to 2, because it's just the size of the maximal independent set in my graph. So the dependent tree has size 2. Okay, so if A is empty, what is the rank of E minus the rank of A? So x minus 1 squared, and what is this thing? 0. Okay. Now, A could also be 1, 2, or 3. Right? It could be a 1-element set. And then, what is this thing going to be? 1. Okay. 2 minus 1. That's 1. And what's the second thing going to be? 0. Okay, so there is still, we don't have y minus 1. Okay, and since there's 3 possible sets, I need to add a 3 in front. And then I can also have 1, 2, 2, 3, and 1, 3. And what are going to be the exponents? 0 here. And what about here? Also 0. So just 3, plain 3. And finally, I have 1, 2, 3, a single set. Then this is going to be what? Also 0. And then this is going to be 1. Okay, nice. Y minus 1. Does it work or not? Let's see. I mean, let me actually. X squared minus 2x plus 1, 3x minus 3 plus 3 plus y minus 1. And hopefully, so this is x squared plus x plus 1. Wait, hold on. 1 minus 3 minus, okay, plus y. And yeah, so notice that this formula gives you lots and lots of cancellation. But it is a formula. You can, now how do you prove? So far I have 2 theorems. One theorem is this formula. Another theorem is that this polynomial is well defined. And you can prove them together just kind of simultaneously. Just check that this formula satisfies the deletion contraction recurrence. For every choice of an edge, E, this just does the job. So once you guess the correct formula, everything like checking the deletion contraction recurrence is easy. All right. But still, this is slightly unsatisfactory because of how many constellations we get. So let me actually make an observation. This polynomial, or more generally, remark. More generally, the Tutte polynomial, if you just look at the recurrence, it has positive integer coefficients. At no point am I subtracting or dividing or just, this Tutte polynomial has positive integer coefficients. And how many terms should I expect? If I just plug in 1 and 1, yep, 1 term. Well, actually, here I'm going to get 3 terms. What is the number of what? I can hear the last word of monomials. Right, yeah, so what's the total number of monomials? In terms of the actual matroid. Yeah. Yeah. Right, okay, but well, actually, I see. So you're saying if I plug in x and y to be 1 here, then this is going to vanish unless both of these exponents are 0, which means A has to be a spanning tree, or more generally, a basis of my matroid. That's initialization is actually the number of bases of my matroid. And you can also just look it up here. If I plug in 1, 1, I get number of bases. So so there should be a formula. So there should be, we should look for a formula of the following form. That polynomial of x comma y is equal to the sum over all bases, and then just x to some power question mark and y question mark of I, y to some other function of I. So in other words, if for every basis element, you tell me the power of x and the power of y, so that the total polynomial is just the sum of these polynomials. That's the thing that should exist, right? Because if you have a polynomial with positive integer coefficients and it has this many monomials, so clearly there should be a formula like this. How do I find a formula like this? Well, I'm going to tell you a formula like this. But it's going to be slightly unexpectedly weird, but interesting. So it's going to be in terms of what is called internal and external activity. So why is it going to be weird? So let's say you take a Matroid. Be a Matroid. Then what I want to do is I want to choose a total order on the ground set. Choose a total order on the ground set. So a priori, E is just some, a bunch of vectors, so you don't really expect any natural order on them. So you choose one. So it could be like n factorial different orders. You choose either one, and then you make the following definition. Let's say you take a basis. So there's going to be two parts of the definition. First of all, an element of your basis I is called internally active. Yeah, let me just write it down. So if you cannot find a smaller n element j, I prime less than I, such that I without I union I prime is a basis. Okay. So you look through the elements of your basis and you see, for each one you check, like, can I replace I with something smaller and still get a basis? If the answer is yes, then it's not internally active. And let me also mention the dual notion of external activity. So let's say if you take an element j, which is not in your basis, and then I'm going to call it externally active if there is no j prime less than j, such that so j is already not in my basis. So I want to remove j prime, add j, and get a basis. So that's the definition. And yeah, and just by definition, for a given basis I, int of I is the number of internally active elements of I, and ext of I is the number of externally active elements. For example, let's say I do some random example. And then you're going to tell me what is the, say, I have a double H here, and then a loop. And then, so I'm taking an example of a graphical matrix. So I have to, what's the first step? I have to choose a total order on the edges. I have to just number my edges in some way. Let me do this kind of randomly. 1, 2, 3, 4, 5, 6. Okay. So 1 is less than 2, and etc. Now I also want to choose a spanning tree. So let's say I choose, because I is a basis, which in this case is going to be a spanning tree. Maybe I choose 1, 6, and maybe 4. I is 1, 4, 6. Now, let's see. Which of these elements are internally active? 1, 4, 6. Is 1 internally active or yes? Yeah, actually 1 is like no matter if it's in my set or not, it's always either internally or externally active. So there's nothing less than 1. So it's internally active. What about 4? What? No, why not? Yeah, you can replace 4 by 2 and still get a spanning tree. So 4 is not internally active. How about 6? No, why? You can replace 6 by 5 and still get an internally, you still get a basis. Okay. If I try to compute external, so I need to look at the complement 2 and 3 and 5. Is 2 externally active? Yes. Why yes? You can replace 4 with 2. But that's actually, hold on. So 2 is j in this case. Right. So if j is 2, then j prime has to be 1. But then replacing 1 with 2 is not going to give me a spanning tree. So 2 is externally active. Yeah, these are very easily confusing. How about 3? It's a loop. So you can't really remove anything and then add 3 to make a basis. So a loop is always externally active if it's not always externally active. And what about 5? Nice. Okay, right. So if j is 5 and j prime is 1, then I remove j prime, remove 1 and add 5 and still get a basis. 5 is not externally active. So in these two statistics, internal of I is equal to 1 and ext of I is equal to 2. That's basically the answer you get for every basis of your matroid. So here's a theorem. Basically, the Tutte polynomial of your matroid is equal to the sum over all bases of x to the int of I times y to the ext of I. So that's the desired formula. You get only positive, you get a positive sum of exactly basis the element. Right. So it's a great observation, right? If you fix I, then these numbers actually depend on the ordering quite a bit. Yeah, let me even down. So these two things depend on the choice of the ordering. But the whole polynomial does not depend on any choices. So again, magically, no matter which ordering you choose, you can actually choose some convenient one in practice. But yeah, the result does not depend on it. So you have to break the symmetry, and then you get a positive formula. But and then that happens quite a bit in combinatorics. So yeah, let's try an example. Let's say G is my graph as usual, the complete graph on 3 vertices. Then I want to compute its Tutte polynomial using this formula. So let's see, how many bases do I have? 3. Okay, 1, 2, and then 1, 3, and 2, 3. And then I need to compute, let's say for this term, I need to compute internal activity and external activity. So is 1 internally active? Yes. Yeah, 1 is always active. Is 2 internally active? Is 3 externally active? No. Because you can replace 3 with one of these guys and still get a basis. So therefore, this gives me x squared times y to the 0. Okay, here I have 1, 3 in my basis and 2 not in my basis. 1, as we mentioned, is always active. 3 is not. You can replace 3 by 2. And 2 is not because you can replace 1 by 2. No, so this is going to be x. Yeah, so we can replace 3 by 2. That's why 3 is not. No, for 2, you have to find something smaller than 2. Yeah. So this is x to the first and y to the 0. Finally, here, I have 2, 3, 1. Is 2 internally active? No, you can replace 2 by 1. Similarly, 3 is not internally active. 1, as we know, is always active. So this here, we're going to get y first, x to the 0. That's the I think there is a proof which you kind of any two orderings differ by some simple transposition, right? You can just kind of change the instead of 1 and 2, you replace them by 2, 1, and then so you can check that. I think that you can always whenever you have some simple transposition, then there is some easy bijection that shows that this formula is the same. Yeah, but in general, if you have two different orderings, the bijection is going to be a composition, which is tricky in general. So yeah. So this formula is very efficient if you use a computer. Just you get as many terms as your polynomial, especially compared to this formula with huge cancellation. So yeah, finally, what happens if I take the dual of my matroid? And I want to compute the Tutte polynomial. What am I? You have to switch x and y. Nice. And why is that? Right. Yeah, so if you just look at these two definitions, taking complements of basis exactly switches internal and external corollary. And in general, so yeah, let me just summarize. If you apply matroid duality in this context, then what you get is you switch deletion with contraction and vice versa. And loops become co-loops and vice versa. And corank, so we had this formula for the corank and nullity. Corank becomes nullity. And finally, internal, as we just mentioned, internal becomes external activity. So yeah, all these notions for Tutte polynomials are actually quite sort of self-dual in a sense. Yeah, and that's basically any questions on Tutte polynomials? Right, yeah, so that's a good observation. So the number, for example, spanning trees of your original graph, if you have a planar graph, it's like the planar dual, then the spanning trees of your graph are in bijection with by taking complements with the spanning trees of the planar dual. And the forests are indeed in bijection with connected subgraphs of the dual. Yeah, these are actually not quite easy. Acyclic orientations and strongly connected orientations. Yeah, these are nice exercises. You can try finding bijections at home. I mean, it's easy to check that all these satisfy deletion contraction, but yeah, for planar graphs and their duals, these are actually, yeah, I have to think about why like these are in bijection for. This is, I mean, you have to, I guess if you have an arrow in the original graph, then for the planar dual, you can choose sort of an arrow which makes a positive orientation with whatever. This is probably going to work, but I have to, I'm not sure. Any other questions? Oh, by the way, I should announce there's homework due this Friday, in case you didn't get any emails. Homework, and oh, another thing I forgot to mention is that when we were discussing duality for realizable matroids, I mentioned some proof using Grossmanian orthogonal complements, and yeah, I think it works over any field. There is a problem in your homework which proves that, but yeah, basically, I think what I said was correct, that you take just usual orthogonal complement. It can be the case that a vector can become orthogonal to itself over a finite field, but it's fine. All right. So one other thing I want to mention is, well, basically the rest of these lectures, I'm going to try to relate matroids and oriented matroids to things we studied previously. So now I want to relate matroids to polytopes. Matroid polytopes. And so you start with the matroid. Matroid of rank, let's say K. And let's say E is your ground set is just bracket N. How do you associate a polytope to such an object? Well, yeah, I mean, I can ask you to guess, and you can make many different guesses. So let me just write down the definition, which is quite natural. Matroid polytope which is denoted P sub M, is just the convex hull of the basis. So more precisely, you take all possible bases, and then you take, for each basis, you take the corresponding 0, 1 vector. P sub I, the sum over I in I of the standard basis vector. So you get a polytope. And let's say I take the the most interesting example here is the uniform matroid. So remember, uniform matroid is the one where you get all the, and just any k element set forms a basis. So yeah, that's a good question, and yeah, I'm going to ask that question in a few minutes. So yeah, but first of all, let's even consider the special case where all, like each I is a basis. So then what is the polytope? Hypersimplex, very nice. Delta k comma n. Right, just by definition, this is the convex hull of all 0, 1 vectors with k ones. Okay, so in particular, all these points are vertices. I mean, are among vertices of some polytope. So if you take any other matroid, yeah, let me actually write it down. In general, the set of vertices of the matroid polytope is contained inside the set of vertices from the hypersimplex. And each basis gives you a vertex. Because all these points are already in convex position. So if I give you a polytope, how can you tell if it's a Matroid polytope or not? Any ideas? Say it again. Okay, so you want the lattice of flats of your Matroid to relate to the face lattice of the Matroid polytope. Actually, I don't think it's like, for instance, here the vertices are bases, but I don't think you get base. You can see bases from the lattice of flats. Yeah. What am I? Yeah, these are. Yeah. Anyways, no, you're not asking too much. Please ask lots of questions, and yeah, the more the better. Okay, so here is what I think a cool theorem, an easy way to tell a Matroid polytope from all the other polytopes. And it's again due to Gelfand, Goretsky, McPherson, Serganova. And let's say you have a polytope. Then P is a Matroid polytope for some Matroid M, if and only if and only if the following two conditions are satisfied. First is that it has to be a 0, 1 polytope, so the vertex set should be a subset of the vertices of the cube. And second of all, the crucial condition here is that every edge, each edge of P is parallel to the vector EI minus EJ for some I not equal to J. When is it combinatorially equivalent to a Matroid polytope? Yeah, I don't know. I don't know how to answer that. But you're saying this is unsatisfying. And I guess maybe I agree with you. But what is, though, satisfying is that this is like the exchange axiom. But it's like this is much easier to check than the exchange axiom. So for the exchange axiom, you would have to, like, what's the naive algorithm if I give you a polytope like this? You read off all the vertices, look at their coordinates, these are bases. And then for every two bases, you have to check the exchange axiom. That's way too much work. Here, on the other hand, you only need to look at the edges. If you look at the edges, and then you're done, basically. So somehow, knowing which pairs of bases form edges is somehow extra information which you can use to check that it's a Matroid polytope. So let me try an example. Let's say I take an example for k equals to 2 and n equals to 4. There's actually, you can say a lot of interesting things about Matroid polytopes, and there's a whole bunch of recent research on subdividing the hypersimplex into different kinds of Matroid polytopes. Yeah, there are some interesting directions here. So let me just give you an example. So let's say I draw the octahedron. This is the hypersimplex delta 2, 4. So its vertices are labeled by 1, 1, 0, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0. Just all possible entries k vertices. And okay, so is this whole thing a Matroid polytope? Yes. Let's see. So now we have to look at all the possible edges. If I choose any edge, you see that like to go from here to here, I have to subtract e2 and add e3. And I mean it's symmetric, so every edge kind of looks like this. Okay. Now what if I want to look at other Matroid polytopes? They're going to be subsets of the. I have to choose a subset of vertices and take the convex half. So let's say I remove one. Let's say I remove this vertex. So I get a square pyramid. Is this a Matroid polytope? Yes. Why? Yes. Right. I haven't created any new edges. Yes, satisfies this definition, this theorem. Okay, so this is a Matroid polytope. What if I mean, all the vertices are symmetric, so I can remove either one and get a Matroid polytope. What if I remove two vertices? Let's say I remove this one and that one. I get just 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1. Is this a Matroid polytope? Why, yes. Okay, I still haven't created any new edges. Even though the dimension is smaller, may look tricky, but yeah, the dimension doesn't matter. What matters is the directions of edges. Yes. What if if I take a face, 1, 1, 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, also yes. So can I just take anything, or what should I take to get something that's not a Matroid polytope? Okay, remove something from the base of the pyramid. Let's try that. So let's say I remove this guy. Good. I have created a new edge. It's of the form 1, 0, 1, 0, 0, 1, 0, 1. This is a bad edge. Doesn't satisfy that condition. So this is 1, 1, 0, 0, 1, 0, 0, 1. This is not a Matroid polytope. Do you see any two bases which violate the exchange axiom? Okay, so these two violate the exchange axiom. Why? Is that easy to see? Wait, okay, so exchange axiom tells me that if I have for any two bases I and j, there exists, and for any I in I, there exists a j in j, such that I plus I in j is a basis. Okay, so you're saying I cannot add this one to this space here. Yeah, but what do you have to tell me I and j and little I. Okay, this is okay. So if I try to replace, if I want to remove this one, then I can add this one and get here. Little I is here. So if I remove one, I can add this one here and get a basis. If this is I, right here, I remove it, and I can add either this one or this one, and yeah, that violates. Thank you. Okay, that's good. Indeed, this is not a Matroid polytope. But yeah, the whole purpose of this computation was to demonstrate just how satisfying the theorem actually is in terms of computations. So the methahedron is not a Matroid polytope because it's not doesn't have vertices of this form. Yeah, but there's a class of what is called generalized permutahedra. So for the permutahedron, it is true. The second condition is true. Every edge of the permutahedron is of this form. And there is a class of generalized permutahedra where you can just look at all polytopes with only the second condition. You can say a whole lot of, there's lots of research on generalized permutahedra. In particular, Matroid polytopes are special cases of them. So yeah, I'm out of time. If you have any questions, let me know. If not, I'll see you all on Wednesday.